Okay, this is our sixth or seventh video, and we're going to talk about how we can use the ideal gas law when faced with stoichiometry problems. And stoichiometry is just another word for finding out how much of something we have, which we do with the ideal gas law. I'm just going to add that this video is very applicable to the first free response problem you have to do in your packet, so that's a good reason to watch it. So we have our ideal gas law, and last year we mentioned this when we talked about the volume that a gas occupies when you're at 1 atmosphere and 0 degrees Celsius, which is 273 Kelvin. We called these temperature and pressures, we called it standard temperature and standard pressure, or STP, for standard temperature and pressure. It was the secret code. The S stood for standard, and the standard pressure was 1 atmosphere. The standard temperature was 273 Kelvin. And when we plugged these amounts into our ideal gas law for just 1 mole of gas, so if we had here 273, and all I've done in this, I've just manipulated the ideal gas law here to solve for volume. So I divided both sides by pressure. And now if we put these amounts in, these standard temperature and pressure amounts, and we have 1 mole, and R is 0.0821 liters, atmospheres, moles over Kelvin, or mole. Then our volume ended up being equal to 22.4 liters. So you may remember that you were able to use the volume of 1 mole of gas when you were at STP as 22.4 liters. And that works well if you're at 1 atmosphere and 273 Kelvin, and we use this value in stoichiometry problems. But the problem is, your experiments are not always at 1 atmosphere and 273 Kelvin. In the classroom, our labs are not done at 0 degrees Celsius. We're not exactly at 1 atmosphere. So sometimes, instead of using this handy-dandy value, we have to use the whole gas law to figure out what volume is. And in that case, we'll do the same thing. We'll solve for volume, because if we rewrite what I just had there, you can see that the volume of a gas is directly proportional to the number of moles, and it's directly proportional to temperature, and it's inversely proportional to pressure. So the point is, volume, is proportional to the number of moles, and it's proportional to 1 over pressure. So if you have either of these things, you can figure out your volume by using the ideal gas law, and that's what we're going to do. So we have here a sample problem. We're going to use the ideal gas law and stoichiometry to solve it. So this is not in your note packet, so you may want to pause it and just write down this equation in the problem. But automobile airbags, if you're ever in an accident, are inflated by nitrogen gas being rapidly created. And it's created by the rapid decomposition of a substance called sodium azide. And when you're in an accident, there's a system in the front end of your car that causes a tiny shock, tiny little electric spark, and that gives it enough activation energy that it decomposes instantly, very fast, into sodium and nitrogen. And this gas, see, these are solids, this is a gas, this gas then expands, and this is what fills your airbag. So here we want to find out how much gas we need to be safe, to not really get totally crushed in a car accident. So our airbag has a volume of 36 liters, and we want to fill that with nitrogen in an accident. So what we're going to do is we're going to see what we want to write down, what we want to find and what we have, and see how we can make a path from what we have and what we need to find, which is basically what it says right here. So I'm going to make this smaller, and I'm going to look at my problem, and it tells me that the airbag has a volume of 36 liters. So I have a volume of 36 liters, and that volume is for the airbag, and the airbag is going to be filled with nitrogen gas. So this volume is going to be for my nitrogen gas. I'm going to be specific about that because I have 3 different things in this problem. So the sodium azide is not going to occupy 36 liters. It's going to be the nitrogen gas. with a tiny little bit of solid sodium in there. Then, let's see, what else did they tell me? The pressure of the nitrogen gas will be 1.15 atmospheres. So my pressure is 1.15 atmospheres, and that's of my nitrogen gas. And they tell me the temperature of my nitrogen gas will be 26 degrees Celsius, which I'll convert to Kelvin because I'm probably going to use some gas law. So that's 299 Kelvin. Okay, so that's what I have, and what I want to find out is the mass, right, the grams of my sodium azide, which I should have written first. So that's what I want to find out. That's what I'm looking for. So if I go ahead and look at my equation, I want to find out grams of sodium azide, and that's what I want to find out. But I'm given a lot of information about my nitrogen gas. In order to find grams of something, if I can find moles of something, I can find grams. And when I have a balanced equation, that's always a hint that I can relate these substances in moles. Moles of this to moles of this to moles of this. So if I can find moles of sodium azide, I'll be able then to transfer that to grams of sodium azide. And I can find moles of sodium azide from my moles of nitrogen gas. I could work backwards if I could just find out how many moles of nitrogen gas would be produced. Well, I may be able to do that because now I remember I have this ideal gas law, PV equals nRT, and that allows me to solve for number of moles. In fact, I could rewrite this if I wanted to, like that. N equals PV over RT, and I can solve for my moles of nitrogen gas. And if I can find that out, then I can work backwards. For every 3 moles of this, I have 2 moles of that. Find my moles of sodium azide, and then find the grams. So I'm going to do that. I'm going to substitute in and find my moles of nitrogen gas. So let's do it. I have my N equals, my pressure is 1.15 atmospheres. My volume is 36 liters. My R is 0.0821 liters times atmospheres over moles times Kelvin. And my temperature is 299 Kelvin. Okay. So I'm going to use my calculator, which I have to go get to figure out how many, well right now I can just cancel my units. Here I have atmospheres in the numerator, denominator, liters numerator, denominator. I have Kelvin here in the numerator of my denominator and Kelvin in the denominator of my denominator. So my units are going to end up, I have moles here in the denominator of the denominator, which means they're actually in the numerator. So that's good, because my units will be in moles. That tells me this is set up correctly. Now I'm going to do the math to figure out how many moles of nitrogen gas I have. So when I do the math, I find out I have 1.686 moles, and I'm going to leave it like that. Now, my numbers here, up here, I have 2 significant figures, 3 and 2. So eventually, I'm going to round my answer to 2 significant figures, but I'll leave it as 4 right now. So those are my number of moles of nitrogen. This says N2 here. But I need to know grams of sodium azide. So now I need to use stoichiometry. If I have 1.68 moles of nitrogen gas, how many moles of sodium azide made that? So let's figure that out. We have 1.686. Actually, I'm going to give myself more room. So if I have 1.686 moles of nitrogen, and I want to find out how many moles of sodium azide produced that in the reaction, I can multiply that by a molar ratio, and that molar ratio would come from my reaction. For every 3 moles of sodium azide, so you can see if I make it bigger, it's 3 here. Oops, 3. I'll make it smaller now. Oops. For every 3 moles of, sodium gas that's produced, I need 2 moles of sodium azide. That comes from this 2 right here. So if I multiply this, I'll find out how many moles of sodium azide made this many moles of nitrogen. Another way to set this up would be as a proportion. you have 2 moles of sodium azide in your balanced equation for every 3 moles of nitrogen. So if you have 1.686 moles of nitrogen, how many moles of sodium azide will you need? And you can cross multiply and solve for your unknown, which is right here. When you cross multiply, you'll get a math equation like this. So we're going to do this right now. Our moles of N2 cancel. And so we end up with 1.124 moles of sodium azide. Now that does not answer the question because we were asked to find the mass of sodium azide. We found the moles, but we're so close because you can always convert moles to grams if you have the molar mass, with the molar mass. So now I need to find the molar mass of sodium azide. We'll do that in blue maybe, up on the corner. So sodium, I don't have a periodic table handy. It's about 22.9 grams, I think. So we'll go with that. 22.9 grams. And nitrogen is 14.01. We have 3 times nitrogen, so that's 3 times 14.01, which will equal 42.03. So we're going to add 42.03 to 22.9. We get 64.93 grams. So that's our molar mass of sodium azide down here. So let's make this smaller. So now we will figure out how many grams we have of sodium azide. So we know we have, what color should we do this in? Blue. We know we have 1.124 moles of sodium azide. That's from this number. So we can multiply that by the molar mass to find the grams of sodium azide that we have. And our molar mass is, we just found that out, 64.93 grams of sodium azide in every 1 mole of sodium azide. And this molar mass came, we just figured it out up there. So if you do the math here, 1.124 moles, oh wait a minute, see how I have this written in? What's wrong? What's wrong? Huge mistake. I was just going to say let's cancel our units, but if I go to cancel out moles and grams, they don't cancel. I have put this in upside down. So this is one reason why writing in your units can help you realize you have a mistake. I'm going to give myself more room. And now I have rewritten it correctly, and I can go to cancel my units and see that moles of N2 cancel, and this should say, and I wrote in the wrong thing here. See, I'm here on vacation, so that's why I'm totally confused. This is not 1.686. This should be 1.124 moles of NaN3, because that's the substance we're dealing with. Now, moles of NaN3 are in the numerator. That will cancel with this. And we can multiply our math and find out that in our airbag, in order to inflate it in an accident to that volume, we would need 72.98 grams of sodium azide. So, not an insignificant amount. We could also have solved this as a proportion. I'll do that if you like proportions.